Hello everybody, hope you are doing well. This presentation belongs to the part of the course System Control and Automation, focusing on supervisory systems, in particular supervisory control and data acquisition systems, SCADA. Okay, here let me show you what we will explain. First of all, I will a little bit talk about supervisory system and SCADA, the history of a SCADA system, the main components and functions of a SCADA systems, then the architecture of a SCADA system, which includes hardware and software architecture, the different types of SCADA systems, the applications, the advantages and challenges of these systems, and finally we have the references. Okay, let's get started. What is a SCADA, Supervisory Control and Data Acquisition System? SCADA is a control system, or is an industrial computer-based control system, let's say, that uses computers and user interfaces for supervisory management. It is used to get real-time data to track, monitor, and control industrial equipment. Such information, real-time data, is collected via data acquisition devices that can handle the data, analyze the data, store, and finally present the data to the user. Here is a control room of a SCADA system with many monitors to show the real-time events that might happen in many modern industries like energy, oil and gas, water and wastewater, and many more applications. Let me show you a brief story of SCADA system. Before the concept of SCADA, in many industrial plants, the personnel had to manually, control and monitor equipment using push buttons and analog dials. After that, industrial organization started to control equipment over, long distances using timers, relays, to provide some level of supervisory control without needing to the presence of people and personnel at those remote locations. So they provided a limited automation functionality, but there were some issues. For example, the relays and timers were difficult to configure or maintain. So an efficient and more efficient and fully automated system was required. So in 1950, computers were first developed and used for industrial purposes, and supervisory control systems were introduced and used, for example, in oil and gas pipelines and other industrial markets at that time. Then in 1960, telemetry was established and used for monitoring that allowed, for automated communications to transmit measurements and other data from remote sites to monitoring devices, monitoring equipment. And the term of SCADA was coined in the early of 1970s, and that time the rise of microprocessors and other devices increased the ability of enterprises to monitor and control automated processes more than these years. So the advanced telemetry and the term of SCADA emerged in this year. And here I'm going to show you the main components of a SCADA system. As you see, we have both hardware and software here. Actually, SCADA hardware includes data collection devices such as sensors, relays, data processing devices such as programmable logic controller or PLCs, or remote terminal units, RTUs, and data display devices like human machine interface or HMI, or sometimes they call it monitor. And there were also SCADA software that analyze and translate collected data into a useful information to be distributed to the operators. Okay, let's talk about each of these components. The supervisory computers, this first one, as you see, it acts as a communication server between the human-machine interface, HMI, and these remote terminal units and sensors. Actually, a smaller SCADA system have only a single PC, a personal computer that serves as a supervisory or actually master system. But larger SCADA systems have multiple servers, multiple sites for example, disaster recovery and distributed software applications. So the size of the system is important. Then we have remote terminal units or RTUs, and sometimes they called remote telemetry units as well. SCADA, contains physical objects that are interfaced with RTUs. These electronic devices are controlled by some microprocessors and are used for transmitting record data to the supervisory systems. And they also received data from master systems and to control and the connected devices or objects. We have also programmable logic controllers or PLCs that are attached to the sensors to convert the sensor output signal into some digital data. They are preferred over these RTUs because of their flexibility, their configuration, and actually affordability. We have also communication interfaces. A SCADA system can use both wired and wireless communication technologies and maybe different communication protocols to transmit data between operators and machines. So both non-proprietary protocols like Distributed Network Protocol, DNP3, and some of proprietary protocols are also used in certain SCADA systems. And as well as this, SCADA systems utilize either closed local area network, LANs, and also wide area networks, WANs for in these systems. And then we also have human-machine interface, HMI. This actually displays actionable information collected from the network devices, the sensors. The information is often displayed in the form of graphical pictures and representations, or they can also be like data charts, tables, and displayed on an HMI. And operators can also analyze this information and make some decisions based on this information that displayed on the monitor. One of the other components of the system is SCADA programming. SCADA programming in human-machine interface or master station, is used for creating diagrams, maps that provide necessary information during process or when an event failure. Most of the commercial SCADA systems use standardized interfaces in programming, like C language or derived programming language like C++, C#, Python, and other languages. Here is an overall structure and picture of the SCADA system. You see the control room building, which includes a human-machine interface, a SCADA server here, and the plant that you see, it includes the programmable logic controllers, the industrial equipment that are attached to the industrial equipment, and remote transmission units as well here. There are some functions in a SCADA system like data acquisition, network data communication, data presentation, and control. The data acquisition, a SCADA system obtain machine data through network devices and sensors that are connected to a PLC or RTU. So these devices and the sensors measure parameters like speed, pressure, weight, as a raw data. The data is then sent to the PLC or RTU, where it is translated into the comprehensible and actionable information. At the end, the information is sent to an human-machine interface and displayed to the operators, so the operators can analyze and do actions on the data. Network data communication. SCADA data is encoded in protocol format. The previous versions of SCADA system depended on closed proprietary protocols, but the current systems use standard protocols. Sensors and control relays are very simple electronic devices. They are not able to generate or interpret protocol communication on their own, so we need the RTUs, remote telemetry units, to provide an interface between the sensors and the SCADA network. The RTU encodes sensor inputs into protocols format and forward them to the SCADA master. And the RTU receives control commands in protocol format from the master and transmit electrical signals to the proper control relays. The data presentation, as you see here, the normal circuit networks have some indicators that can be visible to control, but in real-time SCADA system, there are a lot of, let's say, thousands of sensors and alarms that are impossible to handle simultaneously. So the SCADA system uses the human-machine interface, HMI, to provide all the information gathered from different devices and sensors. The control here, the SCADA system, takes advantages of various switches to operate each device and displays the status of the control area. Any part of the process can be turned off or on from the control station using these switches. A SCADA system is implemented to work automatically without any human interaction, but in some critical conditions and situations, it is handled by manpower. So it can be also done by human or automatically. The architecture of the SCADA system, we already seen the components of the SCADA system, the operating equipments, the local processors, RTUs, PLCs, master terminals, and personal computers with HMI, and many other components. So we can classify the architecture of a SCADA system into hardware architecture and software architecture. The hardware architecture of a SCADA system can be classified into two parts: the client layer and the data server layer. The client layer caters to man-machine interaction, and the data server layer manage most of the process of data activities. In the hardware architecture, We have a SCADA station that refers to the servers, and it is composed of a single, for example, personal computer. The data servers can communicate with devices through the process controllers like PLCs, RTUs, and the PLCs are connected to the data servers either directly or either using bus or a network. The SCADA system uses the local area network or wide area network. So the WAN and LAN consist of interact protocol used for communication between the master station and devices. The physical equipment like the sensors that connected to the PLCs or RTUs are considered in this hardware architecture. All of the hardware components that we talked about are included in this hardware architecture. Software architecture of a SCADA system. Most of the servers are used for multitasking and real-time databases. The servers are responsible for data gathering and handling the data. The software architecture of the system includes programs that provide trending diagnostic information. Programs, help in managing information like logistic information, maintenance schedules, and details, systematics of specific machines or sensor that troubleshooting guides. Okay, let's see the different types of SCADA systems. The first one is early or monolithic SCADA system or first generation. The second one, distributed SCADA system or second generation. The third one, network SCADA systems or third generation. And finally, IoT SCADA systems or fourth generation. The early or monolithic SCADA system, first generation. In this type of systems, mini computers are employed. The development of these systems can be done when common network services are not available and are out of services. To design of these systems, we need independent systems without any relation to other systems. The data can be gathered from all remote terminal units using a backup mainframe. And the main functions of these first generation systems are limited to flagging processes in crisis cases and to monitor the sensors. The second generation, the distribution of the control function can be done across many systems by connecting with a local area network LAN. The control operations can be performed by sharing real-time data and command processing. In this type of system, the size and cost of each station are reduced, but there were no consistent network protocols here. And you see the data are collected using these RTUs here and sensors. The third generation, the networking and communication of person's SCADA system can be done using a wireless area network WAN system through data lines or phones. The data transmission among two nodes here can be done with the help of Ethernet or fiber optic connections. This type of SCADA system uses PLC to adjust and monitor the flagging operation. Very simple. Once there is a necessary for main choices. The last one, the fourth generation. In this system, system infrastructure cost is reduced by implementing the IoT through the cloud computing. Maintaining and integrating these systems is easy compared with the previous ones. In real time, the condition of these systems can be reported through the cloud computing. Therefore, implementing of algorithms like intricate control can be done, and that are frequently used on usual PLCs. There are many applications for supervisory control and data acquisition systems, SCADA, because they are mainly used to monitor a wide data variety like voltage, temperature, pressure, water level. So there are a lot of applications. For example, power generation and distribution. In this case, a SCADA system used to monitor current, voltage, circuit breaker functions, current flow. Also, it can use in remotely switching off or on of the power grids. For oil and gas industries, SCADA can use for controlling and regulating and monitoring the flow, reservoir status, pressure in distribution pipes, and so forth. For public transport, SCADA can be used for controlling and regulating the subway electricity, the traffic signals, the live tracking of flights, trains, buses. For water and sewage system, the SCADA system can be used by the municipal corporations for controlling, monitoring water flow, pressure in distribution pipes. For industries and building, it can be used to control the central air conditioning, lighting, energy, entry and exit gates, and so forth. And for communication networks, SCADA can be used to monitor and control networks, nodes, servers, and other equipment in a network. The SCADA system provides a lot of advantages. For example, they can improve the service quality and reliability. They can use to ease the monitor large system parameters, and they provide real-time information on demand, and a lot of other advantages that you can study many papers if you are interested in. There are some requirements and challenges for a SCADA system. The first one is complexity. The SCADA system's complexity, results from adding new components like operator stations, computers, networks, and other types of resources. And as well as this, the complexity of a SCADA system comes from the increasing amount of exchange process data and information. To improve the complexity and reduce it, there are some techniques and solutions. For example, decomposition and integration, or breaking down the problem into smaller and smaller pieces, or we can have abstraction or ignoring details of a problem that are not relevant to the system. The next one is scalability. As you know, scalability The next one is scalability. As you know, scalability is the ability of a system to manage a growing amount of work in a capable manner. As you probably know, there is a relation between scalability and complexity, because increased size means increased complexity. The current and new SCADA generation should be scalable in the sense that new client interfaces or components can be added dynamically without impacting the system performance and without shutting down the system and then run it again. We need the reliability in a SCADA system. The main reason for a SCADA failure is the communication network failure. PLCs and computers have low failure compared to communication network. The availability of the communication network should be increased for a more reliable SCADA system. Then we have interoperability, which is a property referring to the ability of devices and systems and organizations to work together, actually interoperate. A major disadvantage of typical SCADA system is their inflexible, static, and often centralized architecture, which largely restricts their interoperability and extensibility of future SCADA system. One of the other requirements and challenges actually is the robustness, because we should never fully trust in the reliability of electronic equipment. It is important to make sure that SCADA systems are designed with a full redundancy and possible some additional levels of fault tolerance. Okay, there are the references that I've used in these presentations. Hope you enjoy this video.